Thanks for coming along. I'm speaking on Venel's behalf, simply because I've partially hijacked this talk. You're all here to hear Leyla speak about her very interesting topic and the work that she's been doing. But the IEEE Instrumentation and Measurement Society have also hijacked this meeting in order for its own purposes, and that was my doing. Because the material that she's presenting, it seems to fit in very well with the goals of our society. So we're very pleased to have two very important people from the IEEE Instrumentation and Measurement Society with us today. The President of the Society, Ruth Dyer, and the Chair of our International Annual Conference, Professor Zolgi. And I would just really like to ask Ruth to say a couple of words about our society, and in particular the conference that we will be holding in New Zealand, in which you are all expected to attend in about 16 months' time. Ruth, can you just say a couple of words, please?
Be glad to. Delighted to be here in New Zealand. We're here to do some preparatory work for the International Instrumentation and Measurement Technology Conference, which will be held here in Auckland in May of 2019. So since I'm understanding from Andrew that all of you are involved in instrumentation and measurement work, right? So how many of you are members of the I&M Society? Anybody here?
Raise your hand. Even if you're not.
Well, we're in the process of making it easier for students to become members because we're doing away with a student membership fee. So again, it would be very easy for you to join. But besides that, we certainly want to encourage you to think about not only attending, but submitting papers for presentation on your work. We'll have a number of things associated with the conference that we think would be of interest to you. The very first day of the conference is devoted to tutorials, and that's part of the registration fee, and we have a number of 2 parallel sessions that are packed on that first Monday for all sorts of introductory material to the field of instrumentation and measurement. So that would be a wonderful opportunity for you to come and meet other people. We also have, as part of our administrative committee, we have both an undergraduate and a graduate student representative to our group, as well as what we call the young professionals, which are those within about 15 years of having received their degree. So we are very interested in having input from our student members. We have meetup sessions as part of the initial opening reception on the second day of the conference. So there's a lot of opportunity to interact. We'll have a graduate student panel as part of the program that's geared to topics that are of interest to graduate students. So there are lots of ways in which you can interact. We're going to have some industry people there, so it's a great way to network and make connections with companies that you might be interested in going to work for. So lots of opportunities, and I want to applaud the work of Gurub and Andrew as part of getting the whole conference organized and prepared. They've just done a fabulous job, and it's a delight to be here to see your facilities. I'm a bioengineer, so it's been really interesting to me to come and look at some of the work that you're doing. Reza, would you like to make any additional comments?
I think well said. No, everything she said I did know. And I serve as the past president of the society, also, as Andrew mentioned, the chair of the board that runs this conference. And it's imperative that we get young people involved, and we've done a very good job. One thing I will add, we have a very soft spot for students in our society. Every bit of money that we make goes to students, other than their regular expenses. So there are opportunities for students, both financially and otherwise, and I highly recommend that you spend a few minutes away from your Facebook pages and go to IMS and see what's available to you, and hopefully we'll see many of you in 2019. We may raise your
paper award that has money associated.
That's right. We may raise your registration fee, but no. But it would be great to see many of you there.
Best students award, best student paper.
Yes, that's what I said. We have a best
types,
student paper
right.
award.
So
Money associated with it.
Okay, thanks Ruth and Reza. So sorry for hijacking our talk here today, but you'll hear more from me over the next 18 months about the value of this conference, and I hope you can all come along. And so I do apologise, Leyla,
No
but we're looking forward to your talk. Sorry.
Okay, so on to the main program. Welcome everyone. I'm pleased to see there's quite a diverse representation, I think, students and people from other faculties as well. So I'm very pleased to present today Dr. Leyla Esfandiari, who's just having a short visit through New Zealand, and I'm glad that she's made the time to talk to us about her research. So Leyla is an assistant professor at the University of Cincinnati with joint appointments in electrical and biomedical engineering, and her work is in micro devices for the analysis of biochemical signals. So Leyla has a PhD in bioengineering from the University of California at Los Angeles. She then also has an MSc from UC Irvine, and she's been at Cincinnati for about 3 years now. So she also has industrial experience working at Honeywell, as well as, I think,
Applied Medical.
Yep. So she comes with a diverse background of academic and industrial experience. So Leyla has won a number of scholarships and awards. I guess chief of which is an NSF fellowship for cell mechanics and a Boeing scholarship. So she's going to talk
Yes, thank you so much for, thank you very much for your kind introduction. Thank you so much for having me here. It's a pleasure to be here, and I'm just so excited to see your beautiful country through the next 18 days that I'm here with my fiance. So we're going through North Island to South Island, and we're going to see quite a few nature and do a lot of adventure while I give some talks at University of Auckland and Victoria University of Wellington. So as you mentioned, my talk today is going to be mostly about electrokinetic microdevices for rapid, label-free, and highly sensitive detection of circulating cancer biomarkers. Before I go to the talk, I want to introduce you my lab a little bit and explain what we do in the lab. We are a fairly new lab at Cincinnati. It's been 3 years that I became an assistant professor there. And after setting up the lab, we are basically working on nanopore sensing for sequence-specific nucleic acid detection. This is a project of my PhD topic. I've done work on biophysics and nanopore sensing back at UCLA under supervision of Professor Jacob Schmidt and Professor Harold Lungbukett in chemical engineering. The target analytes that we're looking at right now is microRNAs. Previously, we did ribosomal RNA, single-stranded DNAs, and we are looking at environmental DNA detection as well. Besides nanopore sensing, there is another project that I'm quite excited about. Is micro-nanofluidics for sorting and biophysical measurements of different molecules and different subcellular organelles. Basically, we are looking at mitochondria and exosomes, and we are looking to understand the physical and biophysical properties of exosome mainly with this project. We've done some fabrication of solid-state pores and nanopipettes in our lab. Besides that, we are getting into modeling and simulation using COMSOL molecular physics to understand the biofluidics or fluidics that is applied on these biomolecules, and do the analysis while we are running experiments. Some other projects that we are involved in, these are like mostly multidisciplinary projects that I have collaboration at UC, University of Cincinnati, and University of Chicago. One is a wearable sensor. I'm just going to quickly mention them. Wearable sensor, wearable switch sensor for detecting cortisol through the skin by using iontrophoresis to extract these molecules through the skin, and having a patch for measuring the cortisol level through their skin. So this is a project with collaboration with School of Pharmacy and Professor Heikenfield at School of Engineering. And this is funded by AFRL, Air Force, the United States Air Force. Another interesting project that we are working on detecting the environmental DNA of this salamander that is in danger. This salamander is actually endangered in the state of Ohio, and we got funded from Ohio Department of Transportation to if we can detect the environmental DNA of this salamander and locate them throughout the streams and make sure that if they want to build dams or bridges and any infrastructure, we make sure that we don't bother this salamander and make sure that they are safe. So we are working on making this portable device for eDNA detection. Another project with Professor Ian Papatsky, he used to be at UC and then he moved to University of Illinois at Chicago. We are combining and integrating nanopore sensing with microfluidics for point-of-care diagnostics. And this project was based on a DOJ, the Department of Justice, for detecting sequence-specific mitochondrial DNA for forensic science applications. So we have quite a variety of projects and applications that we are working on, but my main topic today is going to be cancer biology, and I think I'm quite passionate about these projects that we are working on. Just give you a little bit of background and significance. We all know the significance of detecting early detection of cancer and the cure. 40 million new cancer cases every year was found, and then 8.2 million cancer-related deaths. It happened, and I think it was based on 2014 survey. However, 46% of patients forsake routine screening per year, and the reason for it is that it's mostly because it's the uncomfortable nature of these conventional methods. So if you go through the conventional methods, tissue biopsy is one of the most routine ways to basically diagnose cancers. It's invasive, it's uncomfortable. Also, the imaging techniques are pretty expensive and require bulky and expensive equipment. So patients, 46% of patients, even in developed countries, they forsake routine screening, and that's how that's actually one of the statistics that's coming out from World Health Organization. So there are some new early stage monitoring techniques coming out in past maybe few decades, I must say. So they call it liquid biopsy, and I don't know how many of you heard about liquid biopsy. So basically, you detect these biomarkers that are circulating in your body fluids. It could be in your blood, it could be in your saliva, it could be in urine, and so they call it non-invasive or minimally invasive detection. They call it liquid biopsy because then you don't need to have basically invasive tissue biopsy techniques. Also, it is mostly cost-effective, and it can be used as a point-of-care solution. So a doctor can have these devices in their clinical labs or in a smaller settings to do this detection. So we are mostly focused on looking at these biomarkers, circulating cancer biomarkers that are in your circulating blood or other biofluids. I don't know how many of you are familiar with CTC or circulating tumor cells, but they are actually called as circulating biomarkers in your body fluids. But the main challenge with CTC detection is they are very low abundance in your body fluids. So it's very difficult to locate them and detect them in your body fluids. The other one is circulating cell-free DNA. However, this is because it is single-stranded DNA. It's quite unstable. So if you detect it, there is just a short period of time that you can get the detection. The other very important and new one is exosomes. And I don't know, have you heard about, how many of you have heard about exosomes? Yeah, so most of you know about exosomes, and they are basically membrane vesicles that go through, that's secreted from the cells through endocytosis pathway. So basically they have packed protein, microRNA, and mRNA material inside of the cytosol, inside of the cytosolic material in the exosome, and they have tetraspanning protein molecules and other protein membrane protein molecules on the lipid bilayer membrane. They are around 30 to 100 nanometer in diameter, so they're pretty heterogeneous in terms of the distribution of their diameter and size. They're mostly circulating in body fluids. You can find them in plasma, urine, saliva, blood of all of us, and they actually, they're around like 10 to the 6 per 10 mil exosomes in your body fluid. So they're more accessible compared to CTCs. Also, as I mentioned, they are used as a molecular cargo to shuttle microRNAs, which are gene-regulating molecules, and mRNAs and other proteins. So basically, they are used in cell-cell communication. So as the cell secreted exosomes and it goes through your body fluids, it can go and bind to another membrane protein of the cell and basically deliver the gene-regulating cargoes into the new cell or host cell. Also, another interesting phenomenon of these exosomes is that their biogenesis basically represent the cell of origin mostly, and because they're coming from endocytosis pathway, usually they have the membrane proteins and the cargoes are representing the cell of the origin. So if you understand the biogenesis of the specific population of the exosomes, you can map it back to the cell of the origin. That is quite interesting observation of exosome. So another interesting aspect of exosome is that they have these microRNAs, circulating microRNAs that have been used as a gene regulating by binding to mRNAs. They are quite small single-stranded RNAs, so they call it non-coding RNAs. They're around 20 nucleotide long strands. So they basically bind to the mRNA and they affect the protein synthesis of the cell. So they're working as a gene regulator for the cells. So they can be, so these microRNAs can be secreted into their bloodstream in two different ways. One is an active way that basically they pack into the exosomes and they can be actively released to your body fluids. However, if you have cell death or apoptosis, then they can passively be released to your body fluids as well. So there are two ways that these microRNAs are actually circulating in your body fluids. And they are very interesting as cancer biomarkers. Their overexpression or downregulation, some of these microRNAs, overexpression and downregulation is related to the cancer biology. So with all that said, my lab, we were interested in detecting these microRNAs and exosomes, and I go through a little bit of background on how we were going to detect these microRNAs. The first project that came out of my lab was to detect these microRNAs, circulating microRNAs from body fluids. So before I go through that, I want to explain to you a little bit of the nanopore sensing work that we have done and a little bit of background on nanopore sensing that I've done during my PhD, and we were thinking microRNAs, it would be a nice application when I started my lab. So nanopore sensing basically came out of the Coulter counter principle. I don't know how many of you are familiar with that method. Anybody? Yeah. So basically, I'll just go through it really quickly. So you have an inert membrane, and you have a single pore that is basically larger than the diameter of the molecules that you want to detect. And as you apply pressure difference across the pore or apply electric field, molecules pass through the pore, and as they're passing through the pore, you measure the conductance change across the pore. So when there is no molecule going through, you have open pore conductance, you get a current passing through the pore, and as each molecule passes through, you get a spike signal as a conductance change. But they call it resistive pulse change sensing. So the conductance change as each particle goes through the pore can be measured, and the amplitude of each pulse is exactly proportional to the size of the particle. Also, if you have a charged particle, you can pass them through by applying a potential difference across the pore. If you don't have any charged molecule, you can apply pressure difference. So you can always pass them through the pore, but based on the charge, you can actually apply electric field. And the frequency of the pulses is proportional to the concentration of the analytes. And this video here, let me play it again. It's actually from Bailey's group, Oxford Nanopore, that shows this biological pore in lipid bilayer. And as the particles pass through, you get the resistive pulse, you get this pulses, and the duration of the pulse, it depends on the size of the molecule. And when you get a blockade, you kind of like get a step change in your conductance change. So the advantage of the nanopore detection is that it's detection based on the surface charge, as I mentioned. The physical geometry of the molecule can be sensed, and it's a single molecule sensitivity you can get. It is reagent-free and label-free. However, there are some challenges corresponding to these methods, and one of them is that the fast translocation of the particles through the pore. So as they pass through the particle pass through the pore, the fast translocation or high bandwidth, it can make it challenging for sensing single molecule as they pass through if the molecules are very small. So they were using this technology for DNA sequencing, but the main challenge with sequencing is that fast translocation. So they were trying to basically slow down the DNA strand as it goes through and measure each nucleotide step change as the DNA strand goes through. Also, it requires expensive amplification for amplifying that signal-to-noise ratio. And it's prone to clogging, of course. As you go to the nanoscale, you always battle with clogging issue. So to basically overcome these challenges, during my PhD, we came out with a sort of different type of detection, but based on sequence-specific nucleic acid detection. So in this schematic, you can see that we had a solid-state pore, so we have a borosilicate glass nanopipette, and then the probe substrate that we used was polystyrene beads that were larger in diameter compared to the pore diameter. So if in case of when we measure the electrical signal, when we have an open pore current, we get open pore current and we get conductance, we get current through. As the particle under applied electric field move toward the lower potential, we get a step change, we get a current blockade. So we have zero bandwidth in that case. To get this electron neutrality in our probe substrate, we use this probe molecule called peptide nucleic acids. So the way it works, basically these peptide nucleic acids are synthetic nucleic acids, but they don't have the sugar phosphate backbone, so they are neutral in charge. But they have all the bases that are required to complementary hybridize to the target DNA or RNA. So as the bead with PNA is under applied electric field, it won't move through the pore because it is neutral. As the single-stranded DNA comes and hybridizes to your PNA, the whole system becomes negatively charged and move under applied electric field and block the pore. So we get a yes or no answer in terms of if we have the target or not. So that was the design, and quite experience with that. So this is a summary of our experiment. So in case of the target, when we have the complementary hybridization, as the beads are under applied electric field. What happened here? Okay. So let me just play it again. So when we are applying a positive negative, the beads could come block the pore and we get the conductance change across a step change basically. And when we reverse the voltage polarity, we could open. So we could get this open and close as many times as we wanted. But in case of the control, when we incubated the beads with non-complementary DNA, so we have the PNA conjugated to the beads, but we incubated with non-complementary DNA sequence, we get this transient block. And the physics behind this system was actually quite interesting. Because when we have non-specific binding on the bead when you incubate them with DNA, so they got enough negative surface charge to come and block the pore. However, at the tip of the pore, the electric field is higher, and the gradient of the electric field is very much higher than the rest of the pore. So it will remove the non-specifically bound DNAs on the bead. So the bead became neutral, and then at the same time, because this is a borosilicate glass, the electroosmosis across this pore push the beads away from the pore. So we get this open pore as the beads get close to the pore. You can see that here in this video, as the beads come block the pore without changing the polarity, you can see that the bead by itself move backward. And that's because of the opposing electroosmosis force push the beads away from the pore. We either get no blockade, or we get this transient blockade in case of the control experiment. So to summarize that, we actually could detect anthrax lethal factor using this method with single base mismatch specificity and only 3% false positive. We published this in American Journal of American Chemical Society, JACS. And then later on, we look at how we can increase the limit of detection. We went down to 10 femtomolar detection limit when we increase the length of the DNA strand, since everything depends on the charge, and if we have longer charge strand, we could have less molecules. So the detection limit went down to 10 femtomolar, and we could have a PCR-free detection. So we published this during my PhD, and I said this is a nice transition to detect microRNA now. When I moved to Cincinnati, I started a collaboration with Maria Szczecka. She's a cancer biologist in UC Cancer Institute. And she's interested in these two different microRNAs, microRNA 204 and microRNA 210, that are related to the cancer, the kidney cancer. So basically, in kidney cancer, microRNA 210 expression level get elevated, and then in tumor cells it get elevated, and for normal cells the microRNA 204 is elevated in kidney, but is lower level of expression in the tumor. So we have two different microRNAs that already been correlated to kidney cancer, and we wanted to see if we can use our same method to basically detect them by using sequence-specific nucleic acid detection based on the nanopore sensing. So we conjugated the beads with the PNA, terminated PNA. Then we did zeta potential measurement to characterize this assay, basically. So the zeta potential of carboxylic beads before the conjugation is around 60 millivolt. After the conjugation got lower, so we show that we could actually conjugate the PNAs to the bead. Then after the hybridization of the PNA to the microRNA that was complementary to the microRNA, we noticed that underneath the applied electric field, we could actually see the particles are going into this turbulent motion inside of the pipette, but they cannot reach to the pore, and we could not get any sensing. And that is actually because the opposing electroosmosis that pushes the bead away from the pore. So that was a little bit sad, because I was so hopeful that we could get the detection. And the reason for microRNA not being able to detect microRNA is because they're in shorter strands. So there's less charge per bead when we have shorter strand of DNA. With longer DNA strands, I could get them charged enough that electrophoretic would oppose the electroosmosis, basically overcome the electroosmosis and get the blockade. But with the shorter DNA strand or microRNA strand, we couldn't get them electrophoretically mobile enough to block the pore. So we thought, how about we change the whole scenario, and instead of driving everything with electrophoretically, basically, applying electrophoresis, we apply electroosmosis to get to the sensing zone, and we call the pore as a sensing zone. So under the electroosmosis, all particles should travel to the sensing zone. However, if we have a negatively charged bead at the sensing zone, we should have an opposing electrophoresis. And we thought, like, in that case, we're going to get a step change. However, if you have a neutral or non-complementary DNA molecules, RNA molecules on your bead, we should get a complete step change. So the idea is like we exactly reverse the design because we have a really high gradient of E field at the tip of the pore. So we done these experiments with first with microRNA 204. So in case of the target, we notice that we get this serrated shape, we call it. So we get a blockade, but then it opens up as it reaches to the pore because the opposing electrophoretic can push the particles away from the pore. But in case of the 3 different control experiments, non-complementary RNA, PNA by itself, and negative PNA control, we got this step change. So we could go down all the way down to 1 femtomolar detection limit, and we recently published this in actually Journal of Analytical Chemistry. We've done the same experiments for microRNA 210, and we noticed that the detection limit for our microRNA 210 was actually around 10 femtomolar because of the sequence of the microRNA 210. So we got 97% accuracy on this detection. I think I have a summary slides on that. But to make sure that we are correct in terms of the electroosmosis and electrophoretic, we thought, how about we have smaller size beads that they can pass through the pore, and we look at the dwelling time as they pass through the pore. So in terms of the microRNA 204, because this whole bead system is going to be more negatively charged, they should go through the pore slower, so we should have the longer dwelling time. So in case of microRNA 204, we actually notice the dwelling time here is longer, so we get this nice transient blocks as they pass through the pore. And for non-complementary RNA, when we have some non-specific binding, we could see that some of these have a longer dwelling time, but most of them had spike shake, so they didn't have enough charge, so they go through with electroosmosis and pass through really fast. So then there is no electrophoresis opposing them. And then in terms of PNA only, that is basically neutral, we get these spikes only. So here is actually showing the trend of dwelling time. So for target, we got longer dwelling time compared to the non-complementary RNA and the PNAs, and we had like another control experiment here. So to summarize this project, we make a PCR-free detection based on nanopore sensing. So we are not trying to sequence any DNA, but we are doing sequence-specific detection. For microRNAs, we could go down to 1 femtomolar and 10 femtomolar with 97.6% accuracy, but basically this accuracy came from counting the number of serrated shape compared to the blockade full step change. It has a potential to be used for quantitative analysis based on the dwelling time. So maybe we can figure out the quantitative concentration of the molecules, the RNAs that are bind to the bead based on the dwelling time. And also we have a potential to multiplex this by using 2 different particles with 2 different size. So with 2 different size, the amplitude of the signal would change. Then we could simultaneously look at microRNA 210 and 204 at the same time. So with that, I'm going to shift gear and talk about exosome now. So that was one of the first projects that we worked in my lab first year. And then basically interacting with cancer biologists, I noticed they're more and more getting interested in exosomes in cancer. And as a basically molecular cargo of microRNAs, I thought that was very interesting to understand exosomes and how they work in cancer. First of all, there are a few criteria that relate exosomes to cancer. One is large quantities of exosomes have been seen in tumor microenvironments. They transferring oncogenes to target cell, as we mentioned. They promote metastasis and angiogenesis and tumor growth. Also, they facilitate immune system invasion. So they actually have quite different role in cancer biology. But one of the major drawbacks that I talk to folks at different conferences, in microvesicle conferences and cancer biologists, is that the conventional methods to purify and characterize exosomes is very difficult. So for purifying these microvesicles, they're using differential autocertification. Basically, they're separating them based on their size and density, and they're doing multiple very high, basically ultra high centrifugation, and a series of them in actually half a day or a day. So it takes a while to purify these exosomes from cell culture media or biofluids. And then to characterize them, they're using this nanoparticle tracking analysis, or TEM. There's another way to measure them as TEM, but usually for high throughput analysis, they're using this nanoparticle tracking analysis, which is based on their Brownian motion. So they're measuring the concentration, size, and zeta potential. So this is basically the conventional methods that scientists are using for extracting and characterization of exosome. However, the data that they're getting is not really, they don't match each other. So if one lab has a better centrifugation than the other, then there's an inconsistency in results that came out of different labs. So biologists are coming to engineers and physicists for finding a better way to actually basically purify and characterize exosomes. So I mentioned the drawbacks of the conventional methods are time-consuming, expensive, and at the end you get low purity. So the biggest challenge here is that exosomes have these membrane proteins, and as they go through the endocytosis pathway, they have different characteristics. But however, cells shed some membrane proteins as well that only they have the lipid bilayer. And it is very difficult to purify and separate these two molecules from each other in the body fluids. So the need is to have a technology that is high throughput, cost effective, and require lower sample volume to operate. Also, you need a better selectivity and purity for extracting these exosomes. So we came up with the idea of how about we, instead of looking at their size and density, how about we looking at other physical properties of exosomes to extract them and characterizing them. So one of the ideas that came to our mind was to use their conductivity and dielectric properties to see if we can characterize them and selectively entrap them using electrokinetic measurements. And one of these electrokinetic forces that we are looking at is dielectrophoresis. I don't know how many of you are familiar with dielectrophoresis, but basically it's based on the force that we are applying on the particles when they are inside of a non-uniform electric field. So based on their polarization, you can actually move the particle toward the high gradient of E field or to low gradient of E field. So the way it works, basically based on the volume of the particle, the dielectric constant of the particle related to dielectric constant of medium, you can induce this DEP force to the particles to move them toward lower potential or higher potential. And usually the DEP force is applied by applying the AC frequency. However, to induce this AC frequency, the electrodes has to be sort of close approximity to the particles. But for biomedical application, if we have the electrodes very close to the particle and then particles move toward higher potential or lower potential in the electrodes, then we have surface fouling and we can degrade the biomolecules. So a new method called insulating based DEP has been developing lab on a chip type of the techniques, which is you apply high DC voltage across this channel that has these micropillars or this post fabricated inside of the channel. So what happens is when you apply DC voltage across this post, due to the confined geometry around this post, you induce a high gradient of E field. So you can manipulate particle based on their dielectric constant and dielectric constant of medium toward higher field in the middle or lower field on the side. So this figure shows that all the particles are moving toward negative dP or lower electric field potential as they all line up here. So the advantage of this method is that it is a high DC voltage. It's not actually the advantage. This one is actually disadvantage. That they require high DC voltage, but it is a label-free, and there is no surface fouling induced on these type of devices. However, this high DC volt is not very useful for biomedical applications again. So to overcome this challenge, we came up with this technique using the same nanopipette devices, but instead of sensing, we wanted to this time sort and entrap particles using DEP. So basically, this device has similar characteristics of patch clamp setup. So we have a nanopipette that can go into the cell culture medium or biofluids, and it has a spatial temporal resolution. It can be real time and near living cell entrapment. So the way it works is because it has a very confined geometry, when you apply DC voltage across this pipette, you induce a high gradient of E field at the surface of the pore area of the nanopipette. So also you can, while you are measuring and applying electric field, you can measure the conductance across the pore. So as the particles get entrapped, you can measure the conductance difference at the pore. So you can get some semi-quantitative measurements as well. So this type of devices first was introduced by Clement group in, I think it's in Cambridge, and then they were using the nanopipette for entrapping molecules inside. So they were backfilling the nanopipette, but we came up with the idea of not backfilling the pipette, but however we wanted to entrap particles or molecules that are in the solution outside of the pipette. This technology has a fast basically rapid the detection or entrapment results. We can induce high gradient of E field with low operation voltage of 5 volt per centimeter. No surface fouling happens here. It will be cost effective, and it is sort of easy to fabricate these nanopipettes. So this is a setup that we have in the lab. So basically, we have the fluorescent microscopy that we are simultaneously looking at the particles entrapment by the pore, and then these two PDMS chambers that we have, and we basically have the solution in here, the first one, and we have a nanopipette in between these two. While we are looking at optical measurements, we measure the conductance change across the pore as well, so we get some semi-quantitative measurements. Again, there are 3 different E fields or electrokinetic forces we are looking at. So one is the electrophoresis EP, The other one is electric field gradient, or DEP. And the last one is, again, electroosmosis, because the surface of these pores are glass, and they become negatively charged under applied electric field. So the first set of experiments that we have done, first we did some modeling to see if we can understand what would be the net electrokinetic force across the length of this pipette. We are using carboxylic acid beads as a model system, so they are negatively charged particles. And when we are looking at different electrokinetic forces, and we look at the distribution of the electrokinetic forces along this pipette, you can see that at the net force, this is the green line, is the net force, net EK force. So it's a combination of the DEP, EP, and electroosmosis. You can see that along the length of the pipette, there are two positions that this net EK force actually cross the zero axis, which means that the particles, the net EK force is zero at these two positions. One is right outside of the pore, is around like 0.5 micron away from the pore, and then the other one is right inside. And previous groups show that they could get entrapment inside of the pore. So we are trying to look at the entrapment outside of the pore. This simulation has been done under 10 volt per centimeter, and then we went down to 5 volt per centimeter and 3.3 volt per centimeter. If you notice, I got 5 volt per centimeter. You can see that this basically hump here gets smaller, and at 3.3 volt per centimeter, we get this net force that basically show that the particles should go through the pore and not get trapped inside by outside of the pore. So this was the case when we were having positive and negative voltage polarity in this direction, and we did the same simulations for when we reversed the voltage polarity. In this case, the direction of the DEP is going to be the same, because the DEP depends on the permittivity of the particle to permittivity of the medium. However, the EP, which is electrophoresis, and EOF direction changed, so it switched back. And if you notice, with the opposite voltage polarity, we don't get any net force that crosses the x-axis, which means that there will be no entrapment when we have a negatively charged particles. And we've done some experiments to see if that is true or not. So we have this 500 nanometer carboxylic acid beads that are used in our experiments, and we have these nanopipettes, or micron pipettes, 1 micron pipette diameter. So when we are applying positive and negative, we get particles, fluorescently tagged particles, get entrapped by the pore. However, when we are reversing the voltage, we get no entrapment. And this is the conductance change across the pore. And the interesting part is that we get some conductance step change, but I'm not sure how quantitative is that. So basically, one step change doesn't represent one bead. It represents many beads. So it's kind of like semi-quantitative measurements, and it varies experiment to experiment. So I'm not confident that it's 100% quantitative, but it gives you some sort of indication that you get some entrapment. And let me just play this video really quickly. So when we have, a negative, is there? Maybe I should just turn off the light a little bit, or I don't know. Is it visible, or can you see anything? No. Oh, much better. So when we are applying negative and positive, you can see that particles are sort of floating around, but as soon as we switch back to positive, negative, we get more particles get trapped by the pore. And we did this experiment with lowering this voltage across the pore, and we could see that down to 3.3 volt per centimeter, we still get some entrapment, less but some entrapment. And that was actually not consistent with our simulation results, because our simulation results show that we have to get down to 5 volts per centimeter. But here we could actually experiment show that we could get some entrapment below that voltage. And that's so much better than what is the conventional method, the insulating-based DEP methods that they're applying 100 volts per centimeter. And the entrapment happens very fast, like after 100 seconds of applying this voltage. Another simulations that we done was to see if the ionic strain basically has an effect on our entrapment or not. And we did some simulations with different ionic strains. So we went up from 1 millimolar KCl to 500 millimolar KCl. And we again look at the DEP distribution, EOF, and EP distribution. And this is the main important part, the panel D, which shows the net force, net electrokinetic force that is applied on these particles. And we can see that at 1 millimolar KCl, we should have like the highest net force that basically drag or pull the particles toward the tip and the trapping zone. However, when we did the experiments, we actually seen this trend that didn't match our simulation results. And it was a quite interesting observation, because we could see that at 1 millimolar we get some entrapment, but at 10 millimolar KCl we get the highest entrapment compared to the other salt concentrations. To understand this a little bit more, we actually look at the trajectory of the particles under the microscope, or after we got the videos. And then we noticed that actually not only the salt concentration matters, but the initial velocity of the particle matters in the entrapment effect. So what happened is, there is another electroosmosis flow outside of these glass pipettes, and that induced some initial velocity to the particles. And when we have like a very low salt concentration, in this case this is 1 millimolar and this is DI water, we have a very high velocity at the sensing zone. So probably the particles will move to the sensing zone or trapping zone, but the initial velocity is so high that the net electrokinetic force cannot entrap them. However, in the case of 10 millimolar, it's sort of at the tip, this velocity is kind of in between the higher salt concentrations and lower salt concentration. And that could be the reason that the trajectory of the particles and the initial velocity can have an effect on particles trapping. In the case of the higher salt concentration, we notice that the particles are moving slower, which makes sense as far as the divide length goes. So the 10 millimolar gave us a sweet spot and sweet concentration of the salt to trap more particles and have a better efficiency of the trapping. We systematically examined the effect of pore diameter again. So we did the same simulations for DEP, EP, and EOF, and the net electrokinetic force showed that with larger pore diameter, we actually should get more particle trapping. And that's actually matched our experimental results. With 2 micron pore, we got at 10 millimolar KCl, we get the highest number of entrapped particles compared to the other 2 pores. So it was an interesting observation, because intuitively I thought if we go smaller, we might get actually better results, but that was not the case due to the effect of these 3 forces, that we get better results when we have 2 micron pore. Also, we look at the effect of time to see how, if we waited more than 100 seconds, can we get more particle trap. And we noticed that at 40 minutes, we get a plateau, and we cannot trap more particles after an hour. So there is a saturation per pore. So highest yield was achieved with larger pore. Effective time was around 40 minutes. And single pore yield is pretty bad, actually. It's 0.8%. So single pore can have certain number of particles trapped, and then that's it. So to improve this and have it with better yield, we should have multiplex these pores and have an array of pores to basically simultaneously entrap many particles per pore. That's one of the future direction of this project that we are working on. One more thing that we did with this experiments, we actually look at the entrapment and release in DI water. And you can see that the entrapment in DI water was much faster than the other salt concentration. One of the two of the main reasons is that the direction of the DEP will reverse from negative DEP to positive DEP, and also the direction of EOF outside of the pore at low ionic strength get reversed. However, the direction of the EOF inside would be the same. So if you look at this video, you can see that particles are rapidly getting trapped under positive and negative voltage polarity. And then and I cut, and this is like a few seconds after. But after we reverse the voltage, we can actually release the particle back to the new solution. So this is going to be interesting for downstream analysis of biomolecules in future work. If you want to do proteomic or genomic analysis after entrapment, we should be able to release them back to a new solution. So that has been shown with water solution. So we did all these experiments with negatively charged particle polystyrene beads, and then we moved, so we figured out what worked and what didn't work using this device. So now we moved on to actually entrap exosomes from plasma of healthy donors. So we have this 100 nanometer exosomes in PBS solution at pH 7, and we noticed that the entrapment actually was reversed. So with positive and negative voltage polarity, we couldn't get that much entrapment, but as soon as we reverse the voltage polarity, we could get detection or entrapment. Also, the conductance across the pore has shown some spikes as we get a few exosomes basically trapped by the pore. This is a control experiment with the blank sample, so then we don't have any particles entrapment. This video actually shows that we get some few exosomes entrapped with this voltage polarity, but as we reverse the polarity, we can obviously see that we can get more exosomes from the solution entrapped at the pore. So at positive, negative, we don't see that much, but look at right now as we reverse the voltage polarity, the particles build up at the pore. So that was an interesting observation because the whole voltage polarity changed, and that's because the surface charge of these exosomes are way much lower than the carboxylic beads. So their zeta potential is around negative 11 millivolts compared to carboxylic acid beads that are around negative 60 millivolts. So basically by reversing the voltage polarity, you could extract or entrap them more with electroosmosis compared to the electrophoresis. We done some selective entrapment to just show the selectivity of our device. We have 500 nanometer artificial liposomes that we actually synthesized in our lab, and then we had 500 nanometer fluorescently tagged polyestyrene beads in PBS solution. And we could clearly show that with positive negative voltage polarity, we could get fluorescently tagged charged molecules entrapped, and as we reverse, we get these non-tagged kind of like a black dot liposomes entrapped. And reverse experiments are shown here. So here another video that you can see our selective entrapment. So with positive and negative, we should get all the carboxylic beads entrapped, and they are basically fluorescently tagged. You can see some of them are getting entrapped by the pore, and as you reverse, we can build this basically entrap the liposomes at the tip. It's going to come up. That is. Can you see that it's a little hard to see in this screen, but the negatively charged, basically the black dots are getting more entrapped as we reverse the voltage polarity. This is a very preliminary data that we have done to see if we can basically selectively entrap exosomes from liposomes. And to do that, we purchased these fluorescently tagged liposomes to be able to basically differentiate them. And in PBS solution, we couldn't get any selective entrapment, but at 10 millimolar KCl, it was interesting to see that with negative bias at the base, we could see that liposomes were entrapped, but as we reverse the voltage, as the reverse the voltage, the liposomes get entrapped. So here we go. So at negative and positive, first we are getting exosomes entrapped. It's really hard to see. So basically the black dots are getting more entrapped, and as we reverse the voltage, the fluorescent molecules get trapped. So we could see the whole idea of these experiments were to see if we can do selective entrapment. And based on the charge of the particle and conductivity of them, we could actually show some selective entrapment. And the next step for these projects is going to be to apply this AC voltage and then find that cutoff frequency that we are inducing positive DEP or negative DEP on exosomes and be able to get selectively to entrap them based on their dielectric property. So to summarize these experiments, we done fast entrapments. Around like 100 seconds, we could get some particles trapped. We can actually multiplex that and parallelize through high throughput isolation. Selective entrapment can be achieved by reversing the voltage polarity. Also, these semi-quantitative measurements giving us some sort of indication that we get some entrapment, and we can have a low sample volume of 50 microliter if it's needed. So we are moving toward better isolation and selective entrapment of exosomes from biofluids. With that, I would like to thank my team. This is my students here, Yuxi Zhang. She is my first PhD student that's working on the microRNA experiments. Leyla is working on exosomes. Ankit done some simulation work, and Maria Suzeska is a professor at cancer biology at UC, and Scott Langwin, he is an assistant professor in environmental health that give us exosome sample. Also, I would like to thank our funding agencies, NIH, UC Startup Fund, and Collaborative Research Grant. Also, some of my previous work at UCLA was funded with NSF. And with that, I hope that one day we can actually beat the cancer future by working towards point-of-care diagnostic and early detection. Thank you so much for your attention.
Thank you, Leyla.
Sure.
We have time for a few questions.
Questions, yes.
Sorry, so you did most of the experiment now is still in the sample that you made up. Have you ever tried it in the real plasma?
No, not yet.
But you
So we are
expect to have lots of disturbance.
exactly. So we are basically building this model to make sure that what works with a pure sample, and then we're gradually going to move on to having like a real biofluids or cell culture media, and then with that, I think we have to apply AC voltage to get better selectivity on results. But for microRNA detection, we actually extract those RNAs from cells that have the cancers or not. So, yeah.
Questions?
Yeah.
In the experiments, you're controlling in some way the surface charge of the pits to electroosmosis is controlled?
No, actually, we don't do any surface modification on. We don't do any surface modification on the pipettes, but then because the pipette is made of glass and cyanide groups become negatively charged at pH 7, and they induce electroosmosis. So, you know, first we thought like, oh, we should do surface modification, but actually this electroosmosis help us in many ways. So we don't want to do that, but you can Simonize them and then change the surface property or surface charge. Yeah.
Any other questions? Okay, so we can carry our discussions over to the nibbles and rights, and let's thank Leyla
Thank you
again
so
for a
much.
very
Yeah.